Hello students, in this class we will do another example on flexural member, and in this example the data given are, they have said that you have to design a laterally supported beam. That means the beam is laterally supported. First of all, beam of effective span of 6 meter. So the effective span is 6 meter for the following datas. The datas are given like the grade of steel you have to assume is Fe410, right? The maximum bending moment is given, that is M equals to 150 kilonewton meter. Maximum shear force is 210 kilonewton, and you have to design for the particular beam. So the given data will be like, for Fe410 the value of Fy will be equals to value of Fyw will be equals to 250 ampere, right? So those are the given datas. Now what are the steps? For the first step we need to find out the factored load, and in the second step we have to find out the bending maximum bending moment and maximum shear force. In this case the values are directly given to you. The maximum bending moment and the maximum shear force, those two things are already given to you. So basically these are the step 1 and 2, right? So we will be doing from step number 3. So in step 3 we have to find out the ZP required, from which we can assume one particular section. So ZP required will be equals to M moment gamma M0 divided by Fy, right? M divided by Fy by gamma M0. So we are writing like this. So M is given, gamma M0 is known, that is 1.1, Fy is known. So we can find out the ZP required, and the value of ZP required is 660 10 to the power 3 millimeter cube. So this is our ZP required, right? So we have to find one section whose ZP is greater than this value. So in step 4 we have to assume one section. Let us take ISLB 325 at the rate 422.81 Newton per meter. Let us take this section. The section is having the ZP Z equals to 687.76 into 10 to the power 3 mm cube, which is greater than this value. So obviously we can try with this, right? So this value you can get from IS code IS 800, right? And from SP6 you can find out other properties, geometrical properties of this section. Let us write down the geometrical properties. That is depth, total depth is 325 mm, right? And what are the other thing? The breadth of flange is 165 mm. Thickness of flange is equals to 7 millimeter. Root radius R1 is equals to 16 mm. So from these data we can find out, this TF is equals to 9.8 millimeter for this particular case, and TW is equals to 7 millimeter. So from these data we can find out the depth of the web, small d, that is capital D, minus 2 into thickness of the flange plus root radius. How we are getting this equation I have already told you in the last class. So if you put all the values from there, you can find out the value of small d. This is coming to 73.4 millimeter, and other values z izz is equals to 9874.6 into 10 to the power 4 millimeter to the power 4, and zez is equals to 607.70 10 to the power 3, right, millimeter cube. So those are the datas we are getting, right. In step number 5, we have to classify the section. We have to find out the section classification. To find out the section classification, first of all we have to find out the value of epsilon. Suppose this value is 250 by fy, as because fy value is also 250 for this case, so this value epsilon will be equals to 1, and the ratios b by tf will be equals to b by tf will be equals to 82.5 divided by 9.8. How we are getting that? B is equals to actually bf by 2, so bf is equals to 165. We are getting this as this value is coming 8.41, right. So this value is basically, this value you can say this is lesser than 9.4, right, and the ratio d by tw, depth of the web and thickness of the web, this ratio is 273. Already we have find out, we know that value, and thickness is tw is 7, so this value is coming 39.05, and this is lesser than value of 84. So this value is lesser than this value is lesser than this, so we can say this section is plastic section, right. So this is plastic section. And again you can see on another thing that this ratio d by tw is this, which is again lesser than the value 67 epsilon, as because epsilon is 1, so this is also lesser than this. So we can also say that the shear buckling check for web is not required, right. So web buckling should not may not be checked. Okay, now in step number 6, we have to find out the shear capacity, and the shear capacity is equals to Vd is equals to Fy by root 3 gamma m0 into the shear area, that is depth multiplied by thickness of the web. This you can get this equation clause number 8.4, right. So putting all the values are known, putting all the values we can find out the value of Vd, which is equals to coming 298.5 kilonewton, right. And this you can see is greater than 210 kilonewton. What is 210? 210 is the V, the maximum shear stress given, right? The maximum shear stress given, right? So this is lesser than this value is greater than the applied load, so we can say this is okay up till now, right? Now in step number 7 we have to find out whether this is low shear condition or high shear condition. That means in which way we should design. So to find out that one, we have to find out the 0.6 of VD, right? 0.6 of VD. This is equals to 60% of VD. This is equals to coming 179.1 kilonewton, right? But this value, you can say this value is lesser than the maximum shear stress acting on the beam. So as because this is lesser than this, so we can say this is high shear condition, right? So this is high shear condition. So for this high shear condition we have to design this beam. In step number 5 we need to step number 8 we need to find out the design bending strength by this condition. The design bending strength is basically, which we generally denote with MD, this will be basically MDV for high shear condition, and this is given in clause number 8.2.1.3. this is given, right? And you have to find out the value of MDV for that. The value of MDV is equals to MD minus beta MD minus MFD, right? This equation you will get this equation in clause number 9.2.2, right? This value of MDB is given. Now what are the MD, beta, MFD? We need to know. MDV, you can get this clause MD, where MD is basically the plastic design moment of the whole section disregarding the high shear force effect and considering the web buckling effect. So MD you need to find out by the equation what we have already done in for low shear condition, right? So you have to use the equation for MD in, for this, right? And the value of beta is equals to 2 into V divided by VD minus 1, right? And V and VD, those things are known, that VD is the design shear strength and V is the factored shear force, maximum shear force, right? So this is the value, and MFD is basically plastic design strength of the area of the cross section excluding the shear area. How we can find out those values? Let us see. Now in clause number 9.2.2 you are getting this, and the limitation is given. One limitation is given, that is this value should be lesser than 1.2 ZEZ Fy divided by gamma m0. this should be lesser than this value. First we find let us find out this value, and we will check later that whether this is excluding this value or not. So beta, what we already see, what we already saw, that beta is equals to 2 v by vd minus 1 whole square, right? V, vd, those things are known. The value will be 0.1656. This is the value coming, right? Now md, we already know that the md you should take the equation for the low shear condition, and we have already discussed this equation in the last class. This equation is zpz fy divided by gamma m0, right? So those all the values are known. Just put the values and you will get this value at 156.3 kilonewton meter after converting, right? Now to find out this value mfd, the equation is, you need to find out one another thing, that is zft fy divided by gamma m0. Now fy is known, gamma m0 is known, but you need to find out this term zfd. This zfd is basically the section modulus of the flange only. So zfd, how we can find out? This will be equals to zpz or zp, whatever, minus aw multiplied by yw. Now aw is what? Aw is the area of the wave, right? Area of the wave. Now how we can find out the area of the wave? Suppose this is our I section, suppose this is our I section, so this area will be our area of the wave, right? This value will be equals to this height multiplied by thickness, right? And yw will be equals to this distance, right, from the centroid to this distance. So basically aw is equals to capital D multiplied by thickness of the wave, and yw will be equals to capital D divided by 4, right? If you take this distance, this will be 4. So after putting all those values are known, so if you put all the values, zp is known, those things are known. If you put the values, you will be getting the value of zfd, and this is coming 502.916 into 10 to the 3 mm cube, right? Now if you put this value in this equation, if y is known, gamma m0 is known, the mfd value is coming 114.29 kilonewton meter, right? Now if you put mfd value in that equation, you will be getting the design bending strength. As because we are using the md sign, suppose let us use this as mdv and put all the values in the last equation. That is this equation. If you put all the values in this equation, you will be getting the design bending strength equals to 149.34 kilonewton. Now we have to see whether this is crossing the limitation or limiting value this, right? But whatever, if this value is greater than this or not, that doesn't matter, as because you can see that the design bending strength what we are getting is basically lesser than the applied applied factored maximum bending moment. This is 150, right? So this is lesser than this, so this is not safe, this is not safe, right? So we have to use another section, right? So we have to again go back in our step number 4, and we have to choose another section. Now in step number 4, let us try the new section, that is ISLB 350 at the rate 495 kilonewton per meter. This, so we will be using this. This is Newton per meter. We will be using this. So you will be getting all the values, all the geometrical properties what we have done in the last step number 4. They will be getting all the values from SP6, and the ZP value you will be getting from the IS 800. The ZP value for this is equals to 851.11 10^3 millimeter cube. Obviously this value is greater than our ZP required, so just now find out all the specifications. So the geometrical properties were getting the total depth, breadth of the flange, thickness of the flange, thickness of the web, root radius, and depth, small depth d, that is depth of the web, and I and Z is it. We are getting all the values from SP6 and IS 800. Now we have to again repeat all the steps we have already gone through. That is step number 5. You have to classify your section to find out this one. You have to find out some ratios, that is this. And these are the ratios, and this is again coming lesser than 9.4. This is again coming lesser than 84. So this will be plastic section again, right? And as because d by tw is lesser than 67 epsilon, so the web buckling we may skip, right? We may skip the check for web buckling, right? So basically what we are doing, we are again going through the same steps and taking different section. Why we have taken this section? As because the last section was not sufficient enough to prevent this movement. In this we are again making the value of ZP higher, so that the design bending strength will be higher to resist the bending moment, right? So in step number 6 we need to find out the shear capacity. So in step number 6 we are finding out the VD value, which we will get from the clause number 8.4, right? So this value is by this equation we will getting the value of design shear strength. This is coming 340, which is greater than the maximum shear force acting. So this section is okay for shear condition, right? For this maximum shear force, this is okay. Now in step number 7 we need to know whether this is low shear condition or high shear condition. So 0.6 of VD will be equals to 204 Newton again you can see that this value is lesser than 210, which is V. So this value is lesser than V, so again we are getting the high shear condition. So again we have to find out the design bending strength by the previous formula. So in it, we are getting this equation, and this is from clause number 9.2.2. We are getting this formula, and this should be lesser than this value. So the for this beta value is equals to this. Already we had done those things. This value is, I mean, after putting all the values, we are getting the value is equals to this md value. From this formula we are getting the value of md is equals to this 193.43 Newton meter. And in for mfd you need to find out the zfd, and zfd is equals to zpz minus this equation, and ew is equals to the total depth multiplied by the thickness of wave, and yw is equals to total depth divided by 4. So this zfd is coming this one, and putting this value of zfd over there, we are getting mfd value is equals to this one, and putting all the values of mfd and other values in mdv, we are getting the mdv value is equals to 190.57, which is actually greater. Now this is greater than the moment m, which is acting on the beam. So this is we can say this is okay. And let us find out whether this is crossing the limiting value or not. The limiting value, we are getting this one. So putting all the values zdfy gamma m0, putting all the values, we are getting these values 250.06 Newton kilonewton meters. This, so we can easily say that this value is lower than this limiting one, so mdv will be equals to this one, which is safe. Step number 9 will be check for wave buckling. Though for this condition, for this case, we have got d by dw lesser than this. So we have already told you that I have already told you that for this case the wave buckling check is not necessary, but as because this is high shear case, we may check for wave buckling. Now at the last example we have done the wave crippling part, how to check for wave crippling. Now let us find out the how to check the wave buckling. So wave buckling is also happen actually under concentrated load. That means if a point load is acting on the beam or the support reaction, which is also again act like a point load. So at support it may occur, or at the bottom of the any kind of concentrated load it may occur. So we need to first of all find out the area. To find out the area we need to find out the length, right? And the dispersed angle in for this case will be equals to 45 degree. For wave crippling that was 1 is to 2.5, but in this case for wave buckling this will disperse, the load will disperse at 45 degree angle. So we need to first of all find out the lengths like b1 or in this case b, right? Whatever may be the length. To find out b, we can simply do the b plus 2n. N1 is this, and this will be equals to h1. So we can find out the value of n1 using this as 45 degree angle. So sorry, this is a n1 as because 45 degree angle. So if this is n1, this will be n1. So we can find out this n1, and this p will be given to you. Otherwise you have to assume the B is nothing but the bearing width, right? In this case also this B bearing width plus N1. In this case two N1s will be there, in this case one N1 will be there. So whatever may be, you have to find out the value of B or B1, and you have to multiply this with the thickness of the wave and FCD. FCD value you can get, this is allowable compressive design compressive stress in wave, you can say. This you will get from table number 9C. This table number 9C is at page number 42 in your IS code. You can find out in this table. In that table, a table has been given to you, that is for various values of KL by R and various values of Fy, various values of Fy in this direction, various value of KL by R in this direction. For these two cases, various values of FCDs are given. Now if Fy is known and KL by R is known, you will be getting your FCD value from this table, right? So let us take our example. In our example, KL by R we need to find out, and B we need to find out. In our case, as because we are having only UDL, so the wave buckling can occur only under the support, right? Only under this over the support. So suppose we are considering the bearing width is equals to 100 mm, suppose, right? And we need to further find out all the things. Let me write down first of all, then I will explain. So in case of over the reaction, the bearing is, we have assumed 100 mm. So we need to find out this area, that means this length multiplied by the thickness of the weight. This length will be coming the bearing D plus this value N1. So suppose this is capital D by 2, right? So all the values are right now, B, N1, and TW. So we can find out the value of D, which is this. Now we need to find out the rest part. So we have to find out the lambda, that is slenderness ratio, that is equals to KL by R. KL equals to 0.7 into D. R is equals to root over I by A. I is equals to BD cube by 12, that is B into T, thickness of the wave cube divided by 12. Area is the B into TW, thickness of wave. So R will be equals to root over this. If you put all the values, this will be this, and if you simplify this, you will be getting this value, that is TW by root 12. Now either you can put the values over there and over there, and you can find out the value of R, and you can find out KL by R, or otherwise you can find this general formula and you can use this formula in any kind of example. So if you put the KL by R equals to KL equals to this, R equals to this, you will be getting 0.7 into d root over 12 divided by TW. So after simplifying, this will be coming 2.425 D divided by TW. So in this case, if you put all the values D and TW, you will be getting this value, that is 96.7415, and Fy W is known, that is 250. So lambda slenderness ratio is known, Fy is known. So from this table 9C in page number 42 in your IS code, so lambda is denoted in this direction, various lambda values are given in this manner, in this manner, and various fy value given in this manner, and with respect to one certain lambda and one certain fy, you will be getting one certain fcd value, right? So similarly you can find out the fcd value for these and these values. In this case the fcd value is coming 111.55 newton per millimeter square, right? This is the design compressive stress, and that means the capacity, the ultimate capacity of for buckling will be equals to AB area, this area, right, AB into the strength, right, that is FCD. So this is putting the value of AB and putting the value of FCD, we are getting this strength against buckling is 227.00. This is the strength to restrict the buckling. What is the stress which is acting? The stress is acting 210 kilonewton, the maximum shear stress over there, right, over the maximum shear stress over any point, that will be obviously over this support, as because this is simply supported beam having UTL, so maximum shear force will be there. So this value is, we can see that this value is greater than this value, the strength is greater than the acting stress, so it is okay with respect to the wave buckling. Now step number 10, check 10 step number 10, we have to check for wave crippling. And wave crippling, the procedure I have already explained in the last class. We have to use this formula where n1 will be equals to this plus 2.5 into thickness of the flange plus the root radius, assuming that the dispersed uh, at a ratio of 1 is to 2.5, so we will be getting this value. So the n1 value will be this. So if you put all the values, b is the bearing, what we have earlier assumed that bearing will be 100, so bearing 100, n1 is this thickness, and all the values if we put and if we convert this, you will be getting this value as 238.38 kilonewton, which is greater than the maximum shear force, right? So it is also okay in with respect to the wave tripling. So in this manner we can design for high shear condition also. Okay, thank you.